As it's 10:30, it's 10:30. I will now switch to English. And as I can see, George turned off his camera. George, can you hear me?
Yep. How's my audio?
Perfect. I
Great.
can hear you just fine. Great to see you. Thanks for being here. I would like now to introduce George Kamiya. He's an analyst for the International Energy Agency in Paris. He's been working there for 6 years now. He's working on environment, climate change, and new mobility, and he's coordinating the agency's work on tracking clean energy progress and digitalization. I can say I got interested in his work when he published a critique of a study of a French think tank back a couple months ago, which dealt with global streaming and how the media picked it up, and he discussed the role of the media in there, which was not quite right in doing so. So as a journalist, I got interested in that, and I'm curious what he has to say and share with us today. So welcome, George, and the stage is yours.
Thanks. Thanks so much, Mark, and thanks so much for the invitation. It's really great to be here. Sorry, I don't speak German. I'll have to do with English, and hopefully you can glean from the slides the key points and the data at least. So can you see my screen? Just quickly checking. Mark,
Yes,
are you able to see? Okay, great. Okay, so yeah, so I'll try to cover, I mean, I'll talk about the impacts of streaming video on climate change and energy, but I'll also talk more broadly about the energy and climate impacts of digital technologies at large, both the direct and the indirect impacts. So a couple contextual points on the energy sector and greenhouse gas emissions in general is that most of the global GHG emissions come from the energy sector and industrial processes. So that's a key point. The other is that within the energy sector, there's a lot of different sources and services and sectors. So, you know, power generation, we often think of coal and gas-fired power as large emitters. Also, there's emissions from different industrial processes, various transportation modes, buildings, both direct with any gas that we consume and electricity that we consume, but also upstream within the power generation sector that is generating electricity for us. So with that in context, so we have to think about digital technologies, I think, both in terms of the digital direct environmental impacts. So what are the data centers, data transmission networks, devices using in terms of energy, materials, and emissions? And then also, how do those technologies and services induce effects in other sectors? So, for example, you might think about how smartphones and GPS and mobile connectivity has enabled services like Uber and Lyft to do well, and how those technologies in turn could affect other sectors, energy and emissions of our built environment, for example. So these are different layers that we need to consider when we think about the climate and energy impacts of digitalization. So first, I'm going to touch on the direct impacts, the energy and carbon emissions of the ICT sector. So one thing about the ICT sector and digital technologies in general is that it's moving very quickly and growing very rapidly. So if you compare it to, you know, population, which has grown by about a quarter over the last 20 years, GDP, which has doubled, electricity use, which is up almost 70%. But if you look at the number of internet users, that's grown by more than 10 times. And internet traffic has grown by more than 2,000 times. So these are very rapid growth rates compared to other economic and energy indicators that we have. So it follows that, you know, the concerns about the energy and environmental impacts of these digital technologies is growing. So here's a headline from a couple years ago in The Guardian saying that a tsunami of data could consume a fifth of global electricity by 2025, which is not too far into the future. And it's these headlines have actually been around for a long time. Here's another one from 1999 in Forbes in the United States that predicted that the internet would use half of the US electricity supply by 2010, basically in the next 10 years. And that the author of this article argued that we needed to build more coal-fired power plants because the internet would consume so much electricity. So we need to be careful about these projections and what that means for the energy system. But in reality, the latest research actually shows that energy use and emissions from digital technologies has been pretty flat over the past decade. So this paper was published earlier this year by researchers in the US, showing how between 2010 and 2018, energy use of data centers only grew 6%, while internet traffic, data center demands grew several times over. So I'm just going to go into a bit more detail. So between 2010 and 2019, internet traffic grew by about 12 times. Data center workloads, which is a measure of demands for data centers, increased by 7.5 times. But data center energy use was very flat. So it consumes about 200 terawatt hours a year, which is about 0.8% of global electricity use. So definitely not reaching a fifth of global electricity use. There's two main drivers of how this trend, this divergence between demand for data and energy use has been kind of diverging in the past decade. So one is that we've seen a lot of data center workloads, so demand for data center services, shift from kind of traditional so-called enterprise data centers that you might see in a small to medium-sized business, even corporates, who would have a room of servers in their building, which are typically much less efficient, much less utilized. The cooling is going to be done by the HVAC system within the building. So it's a very decentralized system that can be quite inefficient. So with the kind of surge of cloud services that companies like AWS, Amazon, Google, and Microsoft are offering, a lot of those services have been migrating to the cloud. And to hyperscale data centers, so which are much more centralized, much higher utilization, and of course they're going to be a lot more efficient. So that's been one of the main drivers of us being able to use much more data, much more demand for data centers, but keeping the energy demand flat. And our forecasts for the next couple of years show that even with a doubling of demands, we can still maintain around the same amount of electricity. And the other trend is that energy efficiency of computing and of data transmission is rapidly improving. So these are two different studies. One is looking at computing energy efficiency, the so-called Kamiya's law, which shows a doubling of energy efficiency of computer chips over the past few decades. That has been slowing over the past few years, but generally that trend has been quite strong. The other paper from Josh Aslin, including John Kamiya, looked at data transmission efficiency over time, and they've also shown that in well-managed networks, energy efficiency has been doubling every 2 years. So these kind of two main trends have helped to keep ICT energy use demand fairly flat. The other trend is looking at devices. We've seen a huge kind of change in the types of screens that we're using, the types of devices. So think back 10 years when we were using CRT monitors that were consuming a lot more electricity. Now we're using LCDs and increasingly shifting from desktops, which are quite energy intensive, to laptops, even tablets and smartphones. Of course, so one side of that story is energy efficiency. The other side is, how do you power the rest of that energy use? And on this side, the ICT sector has also been doing quite well. They actually account for about half of global corporate renewables procurements over the last few years. And in fact, I think the top 4 companies are all ICT companies, and essentially big data center operators like Google and Facebook and Amazon. Of course, so companies like Apple and Google have made commitments, others have made commitments to reach 100% renewables. Apple and Google have reached that a couple of years ago, and they've maintained that. But I think it's important to know that 100% renewables here means that if they're using, a terawatt hour of electricity a year, they're buying basically enough renewable energy or generating enough renewables to match that on an annual basis. But of course, renewables like solar and wind are variable across time, across space. So just by kind of offsetting and purchasing enough renewables doesn't mean that all the energy that's going into those data centers are perfectly clean. So companies like Google, I think, are thinking about how do they try to match their demand for data center energy use with the supply of clean energy. So this is a map from their recent white paper that shows, in some sites like Oklahoma, the grid is actually very clean. They've perhaps had a power purchase agreement there so that 96% of their electricity is clean. But in situations like in Singapore, the grid there is actually mostly natural gas-fired power. So they're going to either have to build new, wind or solar there, or figure out other solutions using energy storage, other emerging energy technologies. So I think it's an interesting challenge that they've set out to meet 100% clean energy by 2030. So they're going to have to not just procure clean energy now, that they're going to have to figure out, how to green the grid more generally. So it's going to be an interesting challenge. Of course, there's a role for digital technologies here as well. So, for instance, you could use machine learning to better predict when wind and solar would be coming onto the grid, and then shifting some of your workloads to meet that demand. So maybe YouTube needs to tag videos or process them, and some of them might not be time sensitive. So you could shift those demands to the nighttime when there's maybe a lot of wind in Ireland or something. So we've mostly talked about the use phase so far of digital technologies in terms of electricity consumption, but of course there's all these phases that we need to consider when we think about digital technologies, from raw materials extraction of critical minerals to manufacturing phases, which be quite energy intensive, distribution, use, and then of course recycling and disposal. We've talked mostly about energy use and greenhouse gas emissions, but of course there's a lot of impacts from materials extraction. There's air pollution issues, water use issues, and of course electronic waste. So I think these are all things we need to make sure that we're thinking about when we're talking about the environmental impacts of digitalization. So on the point of life cycle for devices, I think it's important to mention that the larger the device, the more the operational phase dominates the life cycle emissions. So for instance, a television, because the energy consumption of the screen is large during the use phase, the manufacturing proportion is quite small relative to the device. But if you look at the smartphone, for example, Apple produces these kind of environmental fact sheets for the different devices. And I think the latest iPhones, about 80% of the environmental impacts come from the manufacturing and materials extraction phase. So, when you're plugging into the wall, the energy consumption is very low. The most of the life cycle energy consumption and emissions are going to come from Apple when they're producing it. So that's why, greening the supply chain is actually very important, especially for smaller devices. Okay, so now I'll touch on the streaming question. So you might have seen headlines like this one: is Netflix bad for the environment? There were German outlets that were quoting this number that a 30-minute show of Netflix emits about 1.6 kilograms of CO2, which is equivalent to about 6 kilometers of driving, which is very high. Here's another headline that I think that said 10 minutes of HD video streaming consumes 5 minutes at a 2,000 watt oven, which, I just did a quick calculation. That means it's consuming 1 kilowatts. So YouTube at 1.5 billion hours a day globally would be consuming 550 terawatt hours of electricity if this were true, which is equivalent to the annual energy consumption, electricity consumption of Germany. Even for Netflix, if we extrapolated this headline, that would result in 70 terawatt hours of electricity, which is equivalent to the annual consumption of Austria. So we need to be very careful about how we interpret these findings, and careful about how we report on them. So if you look on the left graph, you can see that the original Shift project quote that was widely cited in the media, about 6 kilowatt hours per viewing hour, they've actually, since my fact check, they've actually revised their estimate because there was actually an error between how they were calculating resolutions and bit rates. So they've actually brought it down by 8 times, but it still remains very high relative to the estimates that I've done. And of course, these estimates really depend on the types of devices you're using, the resolution, how you're connected to the network. So on the right side, you can see, at least for my scenarios, for televisions, they're very large electricity consumers. So if you're watching Netflix on a TV, your electricity consumption is going to be quite high, but if you watched it on a smartphone at a lower resolution, your electricity consumption is going to be quite small. But generally, most of the electricity consumption, especially for Netflix, where most users are using televisions, is going to come from the user device side.
George, could you
yeah.
just a quick question in between? Could you briefly explain what the Shift project is and what they study on? Because I just to make sure that everybody's on the same page here, because I don't think everybody knows exactly what this is.
Yeah, sorry about that. Yeah, so great question. So the Shift project is an environmental think tank in France. They're widely respected, I think, in France. But they used actually a model from 2015 to do a study looking at the environmental and climate impacts of digital technologies. So one of the problems with using outdated models and assumptions, such as using one from 2015, is that I mentioned earlier that the energy efficiency of computing is improving rapidly, doubling every couple of years. So if, because they used model assumptions from 4 years ago, that can quickly get out of date and result in very high numbers. So they published this paper looking at streaming media specifically last year, and then media outlets like here quoted that number, which was, this 1.6 kilograms per half hour of streaming. And then they kind of took it as fact, and then that's, and then now people think streaming video is worse than driving, so maybe they should drive more or stream less. So it's quite dangerous, I think, to take these factoids without fact checking them. So, I mean, that's one of the reasons why I published this fact check was, just on a gut level, it seemed hard to believe. And I think it's important for journalists to kind of do those kind of fact checks. So for instance, this one, is it realistic that streaming video could consume half as much electricity as a full powered oven? And it's hard to imagine, and you could do a very quick calculation looking at some very high level numbers of YouTube or Netflix just to figure out, is this roughly in the ballpark? And in fact, the Shift project estimate, 6 kilowatts per hour, is even 6 times this amount that was quoted in this outlet. So I think journalists need to be careful about kind of these kind of alarmist headlines and really understand and where those are coming from and try to check, at least on a very basic level, whether those are realistic or not. So so in response to my article, Shift Project have actually corrected their numbers. As I said, they made an error between bits and bytes, which there are 8 bits in a byte. So a very, very basic error, but that was widely quoted by the media. But of course, nobody has picked up on the follow-up, the correction that they've done. So, once it enters the public conscience about something, whether it's the life cycle impacts of electric vehicles or even, something like this, it can color the views of consumers and citizens, even though they might not know exactly where that information came from. So we need to be quite careful about that. And, the conclusion of my fact check really is that streaming video consumes very little electricity relative to other kind of everyday activities, especially driving. So my worry is that if we focus too much on digital activities as large energy consumers with incorrect or outdated information, people might think that other activities that they do, such as driving, which are actually quite polluting, might be okay. And it's a tough communications challenge because, of course, we should all reduce our environmental footprints or carbon footprints in everything that we do. But perhaps if we were to choose, streaming video might not be at that top of that list in terms of the relative impacts. And it really depends what you're comparing to as well. So what's the alternative to not streaming video? Is that, driving to a store to rent or buy a DVD? Or is it to watch broadcast TV, which might actually be less energy intensive? We're working on some calculations around that. Or does it mean that people would drive to the movie theater, which could be very energy and carbon intensive, consume food and facilities there as well? So it's really a question of what is the activity displacing, and then also the rebound effects. I think are very important to consider here, especially for digitalization, where because services are getting cheaper and much easier to consume, we're obviously consuming way more streaming media than we ever have with DVD rentals or any other media. So of course there's going to be more consumption, but the question is how does that compare on an aggregate basis to other substitutes that we have? And we could say the same thing about e-commerce or other things. So I'm going to touch on some of those later. The other point through COVID is that kind of like the data center energy use example, which can still absorb another doubling of data center demand. Turns out the utilization of networks can still be improved such that, for instance, during COVID-19, the lockdown, several telecom operators in Europe actually reported that their energy and emissions were flat, even though their internet traffic on their networks increased by 40, 50% or even more. So these are important things to know about. So getting back to this headline about the prediction about 2025, could this actually come true? And it's really challenging, and it's really important to be mindful about where these predictions are coming from. So this specific prediction actually came from a 2015 paper that actually was the model that was used for that shift project analysis. But the journalists took the kind of highest end estimate of that paper, which was 8,000 terawatt hours, and then said they used that as the headline, even though there were lower range scenarios, and that the author acknowledged that the 8,000 terawatt hour scenario was quite unlikely. And it turns out, so he's actually updated his analysis since 2017, 2019, 2020. You can see that his numbers are going down and down as his efficiency assumptions have changed. There's our analysis with Eric Massenet's analysis at the bottom. But the danger of extrapolating, doing simplistic extrapolations into the future is that you assume certain growth and efficiency unable to keep up, and it results in very high numbers and attractive headlines, but not baked in reality or what's likely, and it really shifts discussions around energy transitions. I think I'll touch on that a bit later. And I think the author of that paper, and we also acknowledge that it's incredibly challenging to predict what's going to happen to digital technologies, in 2025, 2030, even 2040, 2050. So if we think about the past 10 years, we've had different mobile network generations. We've had the emergence of smartphones, which have led to, different applications that are developing. But thankfully, strong efficiency gains, electricity systems decarbonizing to kind of keep those emissions and energy in check. And now we're seeing new technologies like blockchain, machine learning, the Internet of Things, augmented reality, virtual reality, 5G. So all these trends would also, and technologies also have the potential to build additional applications on top. So, if we take machine learning and IoT and 5G all together, on top of that, we could build autonomous vehicles. And that's, that kind of indirect effect that I talked about before, where it's not really just the direct effect of blockchain or machine learning, but what services does it induce in other sectors? And it's very, very hard to predict that. And we need to be careful about predicting longer term trends. In terms of emerging technologies, here's a headline from 2017 that extrapolated this growth in Bitcoin to say that Bitcoin mining was on track to consume all of the world's energy by 2020. We're in 2020, and Bitcoin mining does not consume all of the world's energy. Turns out it consumes about 0.3%. So maybe if you took a certain part of that 2017 number and drew a straight line, that would be possible. But of course, there are dynamics and economics here. So I think it's very irresponsible and dangerous to make those kind of headlines that are not baked in reality. And of course, I think it's a good example here of how quickly the energy use of Bitcoin has actually increased. So, 5 years ago, this wasn't even on our radar, and now it's consuming 60, 70 terawatt hours a year, which is like a small country, like a small European country. Another thing to be mindful of for Bitcoin is that the energy efficiency of mining is becoming very powerful and very efficient. So it's kind of this battle between efficiency and demand again, and how that kind of plays out is going to determine the overall trajectory of energy use and emissions. Now I'm going to talk about direct effects on other sectors. The best example I have here is, what are the energy use and emissions implications of teleworking? So the energy use of digital technologies, your laptop, your screens, is probably similar between your home and your office, depending on the situation. Maybe at home, you're going to use a smaller laptop and maybe less screens. So the real balance actually is going to come from, the energy increase that's going to come from your home energy use and the reduction in energy use for commuting. And those really depend on your climate, your housing situation. If you live in a large house and it's wintertime, you're obviously going to use a lot of electricity or gas for heating. And for commuting, the amount of energy you're going to save is going to be based on what your typical commuting patterns are. So, and your distances. So an American that's driving 40 kilometers a day is going to save a lot more energy than, for instance, me living in Paris, I typically take the metro. So the energy savings on the commute side are very modest for me. The impacts on commercial buildings, on office buildings, is really up to the frequency of the teleworking, I think. If we telework all the time, we can shut down parts of buildings, and that might actually result in energy savings. But largely, if we even have offices at 50%, 20% capacity, it's still going to be using energy for HVAC and all those services. So I think those are harder to determine. And those are direct effects. Kind of longer term indirect effects. They could induce effects such as urban sprawl and people buying larger homes. If, for instance, if you lived in the city and you can telework all the time, maybe you're interested in moving outside the city so that you could own a larger home, have more space. Maybe you would have to get a car. So there are kind of these indirect effects that are also kind of that we need to think about. Same with e-commerce as well. The ease at which we can buy things online obviously saves energy in terms of the commute that we would have to go to the store, but we're going to be consuming more, and the last mile transport energy is just going to go up. A couple of years ago, we wrote a paper, a big report on the potential of digital technologies to be applied in the energy sector. So here we talked about things like smart building controls and thermostats that can better figure out when appliances can be turned on or off, maybe timed with when clean electricity is available on the grid or electricity is cheaper. In transportation, we talked about things like shared mobility services, as well as automated connected vehicles, which I think is one of the interesting examples of where we could see digital technologies have a very large positive impact or negative impact. What I mean by that is automated vehicles, if they're not shared and electric, could actually result in much higher use of automated vehicles compared to today because the costs are going to drop. And if they're all, internal combustion engines, that's going to be a huge problem for emissions, for energy use, for congestion. But if we, figure out good business models and shared services, and we could fit more people in those automated cars, emissions from our road transport sector could actually drop. In industry, we've looked at things like robotics, digital twins, 3D printing, application of machine learning, combined with those, for instance, to accelerate innovation cycles and reduce emissions both during the manufacturing stage as well as the use stage. So, for instance, maybe you could lightweight parts of aircraft through 3D printing. That would lead to less materials used during the manufacturing phase, but also when you're in the air. In electricity systems, there's already a lot of sensors and automations used to improve efficiency of networks and generation. more predictive maintenance. And like I mentioned with the data center example, machine learning can be used to improve solar and wind forecasts so that we can better match when we could use electricity that's clean. In oil and gas, I've seen that machine learning has been applied to reduce costs of detecting methane leaks, which is a very potent greenhouse gas. Even for policymakers, there's a lot of potential here for improving data collection, improving our modeling, improving and assessing our policy options and how effective they are. But all of this and all of kind of the impacts of digital technologies on climate really hinges on whether there are enabling climate policies, I think, to encourage the use of digital technologies to reduce emissions. So, you know, in electricity, for example, I talked about reducing maintenance costs. So, for example, you could use IoT and sensors and ML to extend the lifetime of a wind turbine. But equally, you could apply that technology with, you know, if you wanted, to extend the lifetime of a coal plant, or you could use those technologies to drill cheaper oil and gas and detect more resources and reserves. So without climate policies, my worry is that, you know, the digital technologies are essentially climate agnostic in that they don't really care whether emissions go up or down. But if we don't have the right climate policies to guide those technologies being used in the right applications, I think it could be problematic. A couple wrap-up points. One, looking at the energy sector, is that we have a big challenge with existing infrastructure. So decisions we have made recently and decisions we make tomorrow, such as if we build a new coal-fired power plant in Asia, those could be lasting, you know, until 2070. Those last typically 50 years. So unless they're phased out early, these are huge kind of lock-in challenges with our infrastructure, which is very different from digital technologies, which, you know, tend to refresh every few years and can be are much less bulky, I guess. Similarly, in transportation, a gasoline car that's being produced coming off the manufacturing line could be, you know, driving around in 20 years. So we really need to make good choices now to start to immediately phase out these kind of polluting technologies because of the immense challenge that the lock-in of those technologies could have. The other thing is that in addition to phasing out polluting technologies, we also need, and existing assets, we need to ramp up and scale up clean energy technologies. So I think this is where digital technologies can play a huge role. So, you know, this is our energy technology perspectives analysis earlier this year, where we showed that if we reach net zero globally by 2070, about a third of the emission reductions will come from technologies that aren't yet commercial today. So we need a rapid scale up in innovation. And this gets even more rapid if we look at net zero by 2050, where about half of the emission reductions come from these kind of early stage technologies. If we look at net zero emissions by 2050 for specific industry, for specific sectors that are hard to abate, meaning that the technology costs are very high and that we need rapid innovation in those sectors, specifically heavy industry and long distance transport. If you think of aviation, you know, we don't have the battery technology currently to electrify them rapidly. So it's going to probably have to rely on a combination of electrification, hydrogen, sustainable biofuels. So in these sectors, about 3/4 of those reductions will come from these early stage technologies. And I really think digital technologies has an immense role to play here. So just to wrap up, really two areas I think we need to think about. So one is, how do we reduce the direct emissions of ICT? So everyone can play a role here, whether it's users, whether it's me or you, trying to use our devices for a bit longer, not refresh it so often, watch, you know, our shows on smaller screens. But of course, you know, data scientists, engineers, ML practitioners, they can figure out ways to, you know, conduct their work on more efficient hardware or in regions with efficient low carbon electricity. Of course, ICT companies, like I mentioned, are doing a lot to reduce their energy use with efficiency. I think they need to continue with that and also invest in new emerging technologies and also invest in innovation so that, you know, if efficiency starts to slow down, we have new technologies that can continue that trend going forward. And then the other side is enabling reductions in other sectors. So I think arguably this has the much bigger impact in terms of overall greenhouse gas emissions. So there's roles for everyone to play here, both practitioners, digital technology companies, energy companies, governments, I think will play the absolute central role here. I'm very encouraged to see more and more governments announcing net zero commitments, and I'm hoping that that's followed by really concrete policies that really guide the use of digital technologies in terms of reducing emissions and putting it in the right place. So yeah, I think overall there's a lot of potential for digital technologies. There's a lot we can do to reduce those direct emissions and then enable reductions in other sectors. And we need everybody, whether it's citizens, experts, companies, and governments to do their part for a sustainable future. Here are a few reports that I'd recommend that I've cited throughout this presentation in case you would like to read further. And I'll end there. Thank you.
Great. Thanks a lot, George, for your insights. That was very interesting. First question from me. Are you willing to share those slides? Could you send those afterwards to me so I can share those with everybody?
Yeah, for sure.
Great, great. I have a question here in the chat from Britta Moser. I will read out to you. Mr. Kamiya, thanks a lot for these comprehensive insights. You talked about that greening the grid has to become more integrated in general and globally. What do you make of initiatives like, for instance, Microsoft climate change work? The company plans to wipe out all of its carbon emissions by 2030. We can learn of their roadmap on their corporate hub, but what does that mean? What will it require? And could Microsoft go even further from your perspective, greening the grid and be more sufficient?
Yeah, I mean, it's a great question. So, I mean, like I said at the end of the slides, really, I think tech companies like Microsoft have a lot to do in terms of reducing their own footprint. So, these are these commitments that they've made recently about, net zero, negative emissions, offsetting all their historical emissions, and then also investing in clean technologies. I actually think the direct emissions of companies like Microsoft are fairly modest. So, they have operations, they have campuses, but relative to the supply chain emissions of technologies or kind of broadly thinking about the energy system and electricity systems, they can have a much outsized impact in terms of reducing emissions in other sectors. So I think to be credible in the discussion of reducing emissions in other sectors, it's important that these companies like Microsoft, Apple, Google, Amazon reduce their own emissions to zero, and then also work on how do they apply their technologies in the other sectors. They also have a lot of resources and technology expertise, right? So it's good to see Microsoft, for instance, I think in their announcements have talked about direct air capture and very currently expensive technologies that are much need of investment and innovation to get to net zero by 2050 or 2070. They're going to play some role there. Or hydrogen or energy storage. So I think for them to directly invest in those technologies is very positive. Perhaps the big role they can play is even broader is changing the energy policy discussion and trying to figure out how they can work with grid operators, renewable energy projects suppliers, and governments to decarbonize the grid at large. So not just their own operations, but kind of like what Google is looking at, which is how do they influence energy policy so that their need to have green electricity at a certain location is going to have a positive impact on other users of electricity, other companies that are interested in procuring renewable energy, because in some places the market design of electricity systems doesn't enable, for instance, people or companies to procure renewables in that way. So kind of unlocking that potential, I think they could play a role there.
Earlier on, you talked about how efficient data and energy use has become over the years, or from year to year even. Do you think there's a limit to that development, or will this just keep improving?
I'm not sure. There are far more knowledgeable experts working on this, but from what I've read, at least, that there are certain metrics that are indeed slowing, and of course there's physical limits to the efficiency of a computer chip given our current technology. So I think that's where, you know, they could see a limitation in efficiency in the 2030s or 40s. So I think that's where we can't rely on these current trends to continue inevitably, infinitely into the future. So this is where governments and companies need to invest in these next generation technologies that, you know, get past that those physical limits, or we figure out different ways of computing or data storage, whatever it is, data transmission. We need to start investing now so that those technologies would be available in 2030, 2040, when we start to see, you know, limitations, physical limitations of efficiency improvements that we kind of, so we can't kind of rest on our laurels basically and say, oh, you know, everything has been good till now, so it's going to be good into the future. I think that's a mistake. I think we need to not count on those to continue infinitely into the future, and there's a lot of need for further research and development in that area.
Great.